also prove this by induction. Which imply n plus plus is strictly greater than n, because n plus plus is n plus some other natural number, and at the same time n plus plus is not equal to n. So n plus plus is strictly greater than n. So there is no largest natural number. It's because of this strict inequality we have no largest natural number. If you give me one natural number, its successor is larger. So we will never be able to find some largest natural number. Such a thing does not exist. And this is why you see in one of the remarks that we made after after laying down all the piano axioms, that remark said that the natural numbers can approach infinity. They can grow without any bound. It's the reason. It's one of the reasons. Okay. There is no largest natural number. Okay, now we come to the result that tells us about the relationship between this order relation and addition, and also some of its properties. So this is proposition 2 to 12, and it says all the basic things about order. So accordingly it is called basic properties of order for natural numbers. And there are some subdivisions, some properties are there. Some of them have names. The justification for these names will become clear later on. The first one is, of course, order is reflexive. What the meaning of reflexive is, that will be made clear later when we study these relations in general order relations. That will come within the study of analysis itself. Okay, order is reflexive. Oh, I forgot. I should have taken the numbers first. Let A, B, C be any natural numbers. So the first subdivision says order is reflexive. What it means is this: any natural number is greater than or equal to itself. This is what reflexivity means. Actually, that's not what reflexivity means. The definition of reflexivity is more general than that, but we will come to that later, as I have already said. Then the next subdivision says order is transitive. What this one says, if A is greater than or equal to B and B is greater than or equal to C, then A must be greater than or equal to C. next one, order is anti-symmetric. And this one says if A is greater than or equal to B and B is greater than or equal to A, then they are equal. Okay. There is one more. One more means there are three more. So the next one is order preserves addition. This is the basic relationship between the ordered relation and the addition operation. The fact that we are calling it a relation and the other thing an operation, these things we will come to them later on. Okay. This one says A is greater than or equal to B if and only if A plus C is greater than or equal to B plus C. So it's a double implication. The others you see here, these are just simply implications, or P implies Q, they are of that form. This, however, is of this form, that P and Q are equivalent. This one and this one are equivalent. If one of them happens, the other also happens. The fifth one, it says, it's about that successor, I think. A is strictly less than B. Oh, I should not say less than B. B is strictly greater than A. This is also a double implication. If and only if we have this. Okay. And finally, A is less than B if and only if A is equal to B plus D for some positive natural number. D. We are now going to prove these results. Some of the subdivisions are very easy, others are less obvious. Anyhow, we are going to go through the proof. So for part A, it is particularly easy. A is greater than or equal to A because A is equal to A plus 0. You see, if you look at the definition of this means I must have a natural number C for which A is equal to B plus C. So here that natural number is 0. So that's why by definition A is greater than or equal to A. Okay. So reflexivity has been proved. Now we come to transitivity. Okay, so we are assuming that since this is an if-then statement or implication, the hypothesis I am going to assume A is greater than or equal to B and B is greater than or equal to C. That I am assuming. Since this and this, there exist natural numbers. Let me call them U and V such that First we write the definition of this relation. A is equal to B plus U. Next we write the definition of this one. B has to be equal to C plus V. Okay, so these equations have come from the definition. Then, since we now have an expression for B, we can use this expression here. So A is equal to, in place of B, I can write C plus V plus U. Now, using the associative law of addition, I can write this as C plus V plus U. Now you recall the first result that we proved after introducing addition, that the sum of two natural numbers is a natural number. That will be used here. Since U and V are natural numbers, so U plus V plus U is a natural number. Since V plus U is a natural number, we have, again by definition of order, we have A greater than or equal to C, because A is equal to C plus some natural number. So that gives me this. So we have proved transitivity. Then we come to anti-symmetry. So again the beginning is same. Since A is greater than or equal to B, and but now we have B is greater than or equal to A as well. There exist natural numbers let me take S and T such that A is equal to B plus S, and for this one if I write B is equal to A plus T. Okay, now they imply let me wrap this up completely. Now what do they imply? If I, similarly, just like the previous part, if I use the expression for B here in the first equation, I get A is equal to A plus T plus S. Okay, hence I can write A plus 0, which will be A, which is now equal to A plus T plus S, and using associativity of addition I can write this as A plus T plus S. Now we see, now we can cancel A from both sides, and this is why we need the cancellation law that we proved earlier. Okay, so and what was the result by the way? 2 to 6. No, cancellation law. I forgot the numbering. Okay, let me just call it. So by the cancellation law, we have, you know what cancellation law I am talking about, the one which we have got before. We have got only one cancellation law so far. So this is clear what I am talking about. 0 is equal to t plus s. Okay, cancelling a from both sides of this equation, we get 0 is equal to t plus s. Now here again I can use, oh no, I have this is proposition 226. That was the cancellation law. Now, you see, now we are going to use that result which says that if we get 0 as the sum of two natural numbers, then both of them are equal to 0. And that result is corollary 2 to 9. Now, by corollary 2 to 9, we have t equal to 0 and s is equal to 0. Now we use the value of either t or s in one of these equations and we will get the result. Hence, a is equal to b plus s, but s is 0, so it's equal to b. So that's what anti-symmetry says. If both these relations are true, then a and b must be equal. Okay, next we come to D. Now D, E and F, they are double implications or equivalences. So what D said, A is less than B if and only if. So let me just write that here. We have to prove this. So we have two things to prove. First, we assume this one to be true, we prove this to be true, and the other way around. So assume A is less than B. Okay. Then by definition of this relation, then A is equal to B plus, oh, I think I have I taken C somewhere? No, okay, no, it's okay. B plus X for some natural number X. Okay. If X is equal to 0, then A is equal to B plus 0 is equal to B, which contradicts A less than B. Why? Because the definition of A less than B says this means A is less than or equal to B and A is not equal to B. So if I assume X to be 0, then I am getting A is equal to B, which is not allowed by this, by the definition of this. So it contradicts this relation. So X is not equal to 0, X cannot be 0. So X is positive. X must be positive. Okay. Now, you recall one result we have just now proved. Every positive natural number is the successor of something. So, what was that result? It's because of the numbers of this, numbering of these results that I need this written piece. So, X is positive. Hence, I think it was 2 to 10 or something. 2 to 10, let me just see, okay. Yeah, that was lemma 2 to 10. Hence by lemma 2 to 10, x is equal to say y plus plus for some natural number y. Okay, now we can use that here. Hence, what do we have here? A is equal to b plus x. So we now have a is equal to b plus y plus plus. Right? And we already know that y plus plus is nothing but y plus 1. Okay, this thing we have already proved. Now we are going to use the basic properties of addition. Now, so what I am trying to say here, I have to prove that the successor of A is less than or equal to B. I have written the exact opposite of what I had to write. Sorry about this. This actually means, what was I thinking? B is equal to A plus X. Because B is the larger one, right? B is equal to A plus X. So accordingly, I have to rectify everything, which contradicts this. Okay, now this is okay. So here I have to start with B. This will be A. This will be A. Sorry about this mistake. It happens sometimes. Okay, now using the fact that addition is commutative, I can write this as 1 plus y. Then using associativity of addition, I can write this as a plus 1 plus y. But again, a plus 1 is nothing but the successor of a plus y. So what have I got here? B is equal to a plus plus some natural number. This implies that a plus plus is less than or equal to b. Okay, this is one part of the implication. Assuming this, I have proved this. Now we are going to do the opposite. Yeah. No, I have what the hell am I doing? I have forgotten that. That's why I was thinking I missed something. This is not subdivision D. This is E. I missed that the one which says that addition preserves order or order preserves addition. Okay, let me just do that after we finish this. Okay, next we are going to assume this. Next, assume once this part is over, we can't use anything from here. We are starting afresh. We are now assuming this. We now have to prove this. Okay. Then, this time I am going to be careful. B is equal to A plus plus Z for some natural number Z. from this we have, what do we have? Basically we will carry out the same computation in the reverse order. So B is equal to A plus plus means A plus 1 plus Z. Using associativity of addition, I can write this as A plus 1 plus Z. Okay. So, since 1 plus Z is a natural number, because 1 is a natural number and Z is some other natural number, B is greater than or equal to A. Also, B is not equal to A because 1 plus Z is not equal to 0. Why is that so? If had B been equal to A, then we would be able to cancel A from both sides using the cancellation law. That would give me 1 plus Z is equal to 0. But another result says that if the sum of two natural numbers is 0, both of them have to be 0. But we already know that 1 is not equal to 0. How? Because 1 is equal to 0 plus plus. And we know that 0 is not equal to the successor of any natural number. That's why 1 is not equal to 0. And that is why 1 plus Z is non-zero, and as a result B is not equal to A. So we now have both the things to write this inequality. B is greater than or equal to A and B is not equal to A. That means B is strictly greater than A. Hence, B is strictly greater than A, or we can write that same thing like this. So this completes subdivision E, but I have to prove D also, right? I forgot. Let me do it here, and then we will go to F. Basically in F we don't have to do anything. You will realize why. Now here again this is a double implication. I have to prove that A is it given like that? No. A is greater than or equal to B if and only if A plus C is greater than or equal to B plus C. So here also we have to prove both the ways. Now first assume A is greater than or equal to B. Then A is equal to B plus, you can take anything. Let me just take X itself. B plus X for some natural number X. Then A plus C is equal to B plus X plus C. Using associativity, this is B plus X plus C. Then using commutativity, this is B plus C plus X. Again you use associativity, you can write it like this. So A plus C turns out to be equal to B plus C plus some natural number. Hence, A plus C is greater than or equal to B plus C. Now we prove the other way. Next, assume A plus C is greater than or equal to B plus C. Admittedly, these parts are somewhat, these have started getting somewhat boring. But we have to carefully go through all the steps, because when we come to new things, there we won't have the facility that we already know the things. We will encounter some things which are entirely new. They are this training, you may call it, of going through each and every step logically, that will be helpful there. Okay, so next we have assumed this. Then A plus C is equal to B plus C plus Y for some natural number Y. So C plus A, I can write it as A plus C, which is actually equal to B plus C plus Y. This I can write as C plus B plus Y. I am no longer mentioning what I am using. Okay, the things are self-evident. Here I have used commutativity of addition, like that. C plus B plus Y. So by the cancellation law, we can cancel C from both sides of this equation, from here and here. We have A is equal to B plus some natural number. This implies A is greater than or equal to B. So we have now proved this way also. So this completes the proof of part B, but there is one more part, F, right? Now part F actually, I am going to write something else in its solution or in its proof. To prove this part, go through the proof of part E carefully. What we need to prove in part F is already actually proved in part E. So this part I am leaving like that. You go through the proof of part E carefully and you will see that the things we need to prove in part F, they are already available there. So you just need to recognize the parts. So this completes the proof of our basic properties of order on the set of natural numbers. Okay, but there is one more thing, which is, again there is a result which is also very important. This is also a property of order. It's called trichotomy or trichotomy proposition 2 to 13. Trichotomy of order for natural numbers. So what this says, let A and B be two natural numbers. Okay, by the way, these things that we are going on proving, what is our motivation behind this? That we are putting so much labor in proving these things which are obvious. Don't forget the motivation. We said in the beginning that we are not going to leave anything unanswered. We are going to get to the bottom of everything and we will know why something is true for everything that we are going to see now. That's why we are doing this. So let A and B be two natural numbers. Then exactly one of the following three conditions is true. A is strictly greater than B, A is equal to B, or B is strictly greater than A. Once we are given two natural numbers, you see, in mathematics, when we say two natural numbers or two something, we don't mean two different things. They may be equal also. We just mean two symbols which represent natural numbers. They may represent the same natural number. For example,